When graphing functions, we can look at them in pieces, and the pieces are based on the inequalities shown. So in this example, I have two pieces. So if I was asking you, what is f at 5? I would determine and see that x is equal to 5. Therefore, it satisfies the condition that x is greater than 0. So this is the piece f at 5 is referring to. And my answer would be 8. If I was looking at f at negative 5, I would see that x is less than 0. And so I would be looking at only this rule of that function. And that would be just x. Well, that would just be my input, negative 5. So in piece functions, you're looking at the pieces of the function, and the graph is different for each piece. So let's go further into graphs of functions, and let's just recall the parent functions. We have a linear function, which is just going to be a straight line. And if I wanted to graph it, which I probably should, in standard form, that linear function would be the equation y equals x, and it would go right through the origin with a positive slope. Y equals x squared is a parent function, and that parent function is my quadratic. Notice that it's opening up, and it's what we call standard length. If I'm looking at y equals a cube, that's kind of that chair idea. Again, going through the origin. Y equals 1 over x. This is a function we actually deal a lot with in calculus, and we have a little bit trouble remembering this graph. If you recall, because my numerator is always 1, I'm going to have an asymptote there because I can never get out y equal to 0, and then x can never be 0. So x can never be 0 is a vertical asymptote, y never be 0 is a horizontal. And then we're going to work on shifting those around. A couple other parent functions we need to be familiar with is y equals the square root of x, which is just one wing. I can't have the other half of that wing because then it wouldn't be a function. I know that I have the top wing of this parabola that's laying on its side because I have the positive square root. A couple other ones are y equals log of x and y equals maybe e to the x or 2 to the x. Recall e is just 2.71828. A logarithmic function follows these asymptotes here, and an exponential function is that J curve, and they are inverses of each other. And what we do with these functions is we kind of have these power tools on them. We start shifting them and moving them and so forth. So if I want to shift something to the left or right, notice left and right. If I'm looking on left and right of my coordinate system, left and right is dealing in the x direction. So my shift must be in with x. And if I'm adding versus subtraction, this subtraction is going to move it to the right because you're trying to make 0, and this is going to move it to the left. So it's going to shift these two directions. If I'm going to shift up and down must be with the y because just like my y-axis, it runs vertically. So I take my function, whatever it is, and if I want to move up, I add c. I'm no longer worried about making 0, and if I subtract c, then I will be moving down. And then a reflection, you have two places in which you can reflect. You have a reflection inside with x, and you have a reflection outside with x. Sometimes they don't make a difference because of the square property, but if I'm in with x, that means it's a reflect left or right. So in other words, it's going to go this way or this way, which is around the y-axis. I don't like to remember that. I like to say it's with x, it's going to shift left or right. I don't care about the axes. Here, this negative is outside, so it's going to be a reflect up or down. And up and down would be about the x-axis, but don't remember that because it's confusing about where it's located. So you'll have to know some things about reflections, and that's just a quick little brief review of that.